All right, here's the answer key for the mini quiz that covered Unit 6 and 9. So we have this lovely chemical reaction here. It's for the combustion of propanol, or 2-propanol. And we can see that it's combusting in oxygen. Combustion always happens with oxygen as the reactant. Carbon dioxide and water are the products. We can see that we have this alcohol burner here. So we've got our alcohol, which is the propanol, inside this. And it's burning. It's being scooped up with the wick. And it's burning, and then all of the heat is going to the water. Of course, in an everyday situation, like a real life situation, we're going to have some heat that's going to be, coming off and being lost to the outside environment. But I think in these problems here, we are assuming that all of the heat, all the energy that's released is being transferred from the combustion to the water completely that's in the beaker. So we have some data here. And it says that the mass of the propanol combusted was 0.55 grams. A, calculate the magnitude of the heat energy in kilojoules absorbed by the water. Assume that the energy released from the combustion is completely transferred to the water. So whenever we see calculate the heat energy, that is not temperature. In everyday language, we might say, hey, turn up the heat, and we're meaning turn up the temperature. That's not what we mean in science or in chemistry specifically. Heat is Q, and it's calculated with this equation, where C is the specific heat. You know what? Let's just put it here. Specific heat, this is C. Your M is the mass, so you could either use the mass, or you might need to use the mass of the propanol or the mass of the water. Either of those are masses. We'll talk about which one to use. And then delta T is the change in temperature. So we're going to write this as T final minus T initial. It's always T final comes first, then you subtract T initial. And here is, well, it's telling you T initial and T final. So here's our equation. We have the specific heat. It's specifically talking about absorbed by the water. So all of the data we're going to use is going to relate to the water. So we have specific heat of water is 4.18. We have the mass of water, and then we have the final temperature and the initial temperature. You can't mix up the mass of the propanol with the mass of the water. If you're going to use the mass or the specific heat of water, you have to have the mass of water as well. When you calculate this, it comes out to 15.2 kilojoules. It specifically says in kilojoules, so you're going to need to make sure you convert it. You should have memorized, if you don't already, that 1 kilojoule equals 1,000 joules. Kilo, the K, means 1,000. And on the answer key or the grade rubric, that this question was worth 1 point. All right, so now let's look at part B. Based on the experimental data, if 1 mole of propanol is combusted, how much heat in kilojoules is released? So heat is still Q. However, when we're talking about per mole of reaction, then we're going to look at delta H, which is Q divided by moles. So heat divided by the moles. All of the heat that the water absorbed came directly from the combustion of exactly 0.55 grams of propanol. So the 15.2 kilojoules, that's still the heat that we're discussing here. And it probably should be negative, though it's not exactly, in this context, negative means released. And so since we're describing it as released, we don't have to have our end answer as a negative answer. But if you put the negative number in the kilojoules, that wouldn't, or the negative sign in there, it wouldn't necessarily be wrong. Your delta H could be written as a negative or just described as that much is being released. So you've got 15.2 kilojoules is the Q, and then the moles comes from the 0.55 grams of propanol, and use the molar mass of propanol by adding up all of the elements from the periodic table, and this is how many moles combusted in order to produce the 15.2 kilojoules. So we're wondering in ratio, if we had a whole mole, not just a tiny fraction of a mole, how much would be produced? Well, when you calculate, you've got 1,661.2 kilojoules per mole. And this question here says, report your answer with correct number of significant figures. And in the grade rubric, there was a whole second point that was for the sig figs. So 1 point just got you the correct value. And then the second point was for the significant figures. Typically, they don't tell you which question is the sig fig question because on the FRQ, there's only one of the parts, one of the numerical calculated answers for one of the parts of one of the 7 questions is going to be counted for sig figs. And sometimes it's a whole extra point, and other times you have to not only get the value correct, but also the sig figs correct. And they usually don't tell you which one is the correct, is the one that they're going to grade on the sig figs. But this one kind of did, which was nice. So because we had only 2 significant figures from the grams or the mass of the propanol, then that means our end answer right here needs to be rounded to 2 significant figures. So you can see that the 6 here is going to round the second sig fig up to a 7. So we've got 1700 kilojoules per mole. All right, so this last part is talking about a contamination. If the second student or second experiment is done where we have a little bit of water contaminated in propanol, and that would be easy potentially to happen without knowing it because water and propanol are miscible. That's what this word is here. And that's just because water can do hydrogen bonding and so does propanol, and so they mix in all proportions very easily with each other because of those intermolecular forces that they have in common. So it's saying that the difference of the alcohol burner is still only 0.55 grams of difference. So it would look like we combusted the same amount of propanol, but is the temperature of the water in the beaker, though, not the contaminated water, but the water in the beaker, is that going to have a higher temperature or lower temperature? And the answer would be the final temperature would be less than that measured by the first student because the actual mass of the propanol that was combusted and actually doing the releasing of the heat is less than 0.55. So imagine that instead of being 0.55 pure propanol, you maybe have only 0.45 grams of propanol and the 0.1 grams of water. So if you only had 0.45 grams of propanol combusting, when you plug that into your Q equation, you would actually have less heat, less kilojoules that's going to the water. And that was worth just 1 point here. All right, next question. A student uses a galvanic cell to determine the concentration of ethanol in an aqueous solution. The cell is based on the half-cell reactions represented in the table above. So this galvanic cell, describing it as a galvanic cell, tells you that this is a spontaneous reaction. So that tells you specifically which one of these reduction reactions should be flipped as the oxidation. So when you want a galvanic cell, you want to create a spontaneous reaction, which means you want your delta G to be negative, although this question has nothing to do with delta G, but if you had some information about delta G, you would want to make sure your delta G is negative in order to be spontaneous. But then you also need your E value overall to be positive. So the way we do that is the reduction potential, you're going to look at our volts here. And whichever one is the most positive, or if they're both negative, then you would say the least negative, the one closest to 0. That's the one that is most easily going to be reduced. So this one gets to stay as the reduction half. And the other one is the one that's going to be flipped. The other thing we need to do is we need our electrons to cancel out. And so we need to multiply this second reaction by 3. You do not multiply the volts by 3. So some people did this, and we don't do that at all. You don't adjust your volts except for flipping it. So this one gets to be multiplied by -1 because the whole reaction is being flipped. So then it's a positive 0.085, but your second reaction, its volts does not, or is not modified at all. So all you needed was what I have written in the orange here, where it says write a balanced equation for the overall reaction that occurs in the cell. But the green here is what we have in the two different steps to get there. So first, let's flip our first reaction. So that means you're literally just going to write your products as reactants, which I have here. And then you've got your reactants written as products, which I have here. For the second reaction, we want to multiply by 3 so that the number of electrons becomes 12 because we do not want electrons in the overall reaction. If you end up with electrons in the overall reaction, you have not modified your reactions correctly because you cannot have electrons in the overall reaction of a redox reaction. So what we're doing is we're going to multiply every coefficient by 3 This oxygen gets a 3, this becomes a 12, this becomes a 12, this becomes a 6. So that's why we have 3, 12, 12, 6 before we've canceled anything. We have 12 hydrogen, we've got 12 hydrogens on each side, so that is why I have canceled them. Let's put that back here and here. So we're going to cancel the 12 hydrogens on both sides like I have here. We have 12 electrons on both sides. That's why I've canceled both sets of the electrons. Now, here's the tricky part. We have 3 water molecules on this side and 6 water molecules on this side before we've canceled anything. When you cancel something like this where you've got some of each on both sides, but they're not the same coefficient, you cancel all of the compound from the side that is the lower coefficient, and then you just subtract. So we're going to take 6 minus 3. We only have 3 water molecules left. You do not divide or multiply, you actually subtract. So when you add up this, we've got our 1 propanol here. You've got your 3 O2, and everything else is canceled on the reactant side. On the product side, you've got 2 CO2, and you've got 3 H2O left, and everything else is canceled. So that is why the answer is this way. The grade rubric said that this was you get 1 point for getting the reactants correct and the products correct, and then you get 1 point for it being balanced. So even if maybe you had done something a little bit wrong and you maybe modified our original reactions incorrectly, but if it was balanced, you had the same number of atoms on each side, you still got a point for it. Part B, calculate the E for the overall reaction that occurs in the cell. So E cell is calculated as E reduction plus E of oxidation. And when you're adding, you've got an addition symbol right here. That means that your E of oxidation, that's the reduction potential after it's been flipped. So this would be written as 0.085, our modified potential. So we've got 1.229 plus the 0.085 gets you 1.314, and that is worth 1 point. Part C, a 10 milliliter sample of ethanol is put into the electrochemical cell. This is the same thing as the galvanic cell. Nothing's changed here. This cell produces an average current of 0.1 amps for 20 seconds, at which point the ethanol has been totally consumed, the ethanol that we have put in from the 10 milliliters. Calculate the charge in coulombs that passed through the cell. So we have to remember this nice little equation. I'd have to double check to see if it's on your equation sheet, but you also need the concept of this. Let's look at what I have written in green, which is not necessary for the point here, but just some extra information. So I is equal to current in amps. So this is I, the 0.1 amps. And amps is a unit for current, and it has units of coulombs in the numerator and seconds in the denominator. So we have I is equal to coulombs over seconds, charge over seconds. When we are trying to find charge, though, that means we're trying to find Q. So that means Q is equal to the current times the seconds. So if you can imagine, here's your amps in this one here. You've got coulombs per second, and you're going to multiply it by seconds so that your seconds cancel, and you're left with just coulombs. So you could just kind of, allow the units to lead you to what to multiply or divide if you maybe couldn't remember what equation exactly it was. So 0.1 times 20 gets you 2.0. The 0.0 here is for the sig figs, though this was not a sig fig question. 2.0 coulombs is your answer. All right, so this last question maybe was a little bit tricky, but it involves Faraday's constant. So let's go over it. Calculate the initial concentration in solution. Now remember, concentration is molarity, moles per liter. So we need to find moles, and we need to find the liters. Well, the liters comes from the 10 milliliter sample, so we can just convert that to liters. So that should go here. But first, let's find the moles. So let's remember that Faraday's constant here is coulombs per mole of electron. So we've got 2 coulombs, right, from the previous part. Let's go ahead and put Faraday's law here so that we can cancel our coulombs, and that's per 1 mole of electrons. Well, let's look back at our original reaction here. We had 12 electrons that were being transferred in this original reaction. Every time the reaction happened once, you've got 12 moles of reaction, or well, I guess every time the reaction happens per mole, you've got 12 moles of electrons. So this right here, using 12 moles of electrons per 1 mole of the C2H5OH, that I guess you could also just look at the half reaction up here. Here's our 12 to 1 coefficient. That's the mole ratio we're looking at. That was actually worth 1 point down here in this last part. So the grade rubric said this was worth 2 points. One of the points was for using 12 moles of electrons, and the other one was for just getting the correct answer. So let's look at this. When you find the moles, see our moles of electrons cancel. When you find the moles of ethanol, that comes out to this problem, which that is rounded to correct sig figs, though you don't necessarily have to round right away. Then you just plug it into your molarity equation, moles over liters. You've got your 10 milliliters. Remember, this is something you need to have memorized as well, that 1 liter is equal to 1,000 milliliters. Milli, the lowercase m here, that means 1,000th. And then once you divide, you get 1.7 times 10 to the negative 4 molarity.